Right now, somewhere in the Milky Way, there may be a civilization that has been watching us for longer than our species has existed. Not because we're special, not because we're remarkable, but simply because we are here and space is old enough that being found is just a matter of time. The question scientists are actually afraid to ask publicly isn't whether aliens exist. The question is whether something out there already knows where we are, and whether the gap between knowing and arriving is smaller than we think. What you're about to hear is not a theory. It's not science fiction. It's a genuine, peer-reviewed, physics-backed conversation that researchers are having right now, at actual universities, with actual funding, about what it would physically take for another civilization to cross the space between stars and land on Earth. And the answer is going to rearrange something in how you see the night sky. Think about the last time you looked up at the stars. Really looked. Not just glanced up between texts, but genuinely stood there in the dark and tried to feel the distance. Most of us do it once in our lives, maybe twice. There's a moment where the sheer number of them stops being beautiful and starts being something else. Something closer to vertigo. Every single one of those points of light is a sun. Many of them have planets. Some of those planets are old enough that life has had billions of years longer than we have to get started, stumble, evolve, build, fail, rebuild, and eventually reach outward. Every atom in your body was forged in the nuclear furnace of a star that died before our planet existed. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now. All of it was made in fire and thrown across the galaxy. You are made of the stuff of the cosmos, walking around on a rock, wondering if anyone else is out there. And the thing that should stop you cold is this. If we are here, and we came from the stars, and we're already thinking about how to reach them back, then why wouldn't something else have gotten there first? This isn't speculative dreaming. NASA's Astrobiology Institute, the SETI Institute, and researchers from institutions including Harvard, Princeton, and the European Space Agency have all published work on the physics, logistics, and likelihood of interstellar travel, both for us and for others. The math is real. The constraints are real. And some of the conclusions are deeply unsettling. We're going to walk through the entire question. Start at the beginning, which is the sheer scale of what crossing space actually means. Then move through what a civilization would need to do it. Then through the physics of propulsion, energy, and time. Then through the most haunting thing in all of science, which is the silence. The silence that should be full of signals and isn't. And we'll end somewhere that might change how you sleep. Because the part nobody is talking about isn't whether aliens could reach us. It's how we'd know if they already have. Chapter 1. The weight of the distance. Let's start with the thing everyone says but nobody actually feels. Space is big. Not big like the ocean. Not big like the Sahara or the Pacific or the distance from the Earth to the Moon. Big in a way that doesn't have a human word for it yet. The nearest star to our Sun is called Proxima Centauri. Now, a light year sounds like a unit of time because of the word year in it, but it's actually a distance. It's how far light travels in one full year. Light moves at 299,792 kilometers per second, which is so fast that it can circle the entire Earth more than 7 times in the time it took you to read this sentence. The fastest spacecraft we have ever built is Voyager 1, which is currently about 5 billion kilometers from Earth and has been traveling for over 46 years. If we pointed Voyager 1 directly at Proxima Centauri and kept it going, it would take approximately 73,000 years to get there. Not 73,000 days. Not 73,000 months. 73,000 years. To put that inside your body, modern humans, our species as we recognize ourselves, have only existed for roughly 300,000 years. So the journey to the nearest star using our best current technology would take nearly a quarter of our entire existence as a species. One way. That is the starting point. That is the minimum difficulty. And Proxima Centauri is the closest thing to a neighbor we have. The Milky Way galaxy stretches about 100,000 light years from edge to edge, and there are hundreds of billions of stars in it. Some of the regions of the galaxy most likely to host complex life are 25,000 to 30,000 light years away from us.
On the Voyager 1 timeline, reaching those regions would take longer than written language has existed, not once, but several 100,000 times over. So when people say crossing the galaxy is hard, they're not being dramatic. They're being polite. But here's where it gets genuinely interesting. Because the laws of physics don't actually say it's impossible. They say it's expensive. In ways we've never had to confront before. And that distinction matters, because impossibility closes the door. Expense just raises the price. And there are civilizations out there, if they exist at all, that have had billions of years longer than us to work on paying for it. Think about what humans were doing 10,000 years ago. We were making clay pots. We were learning to plant wheat. We had not yet invented the written word. Now think about where we are now. We have split the atom. We have sent machines to other planets. We have mapped the human genome and begun to edit it. All of that in 10,000 years. A civilization that is 1,000,000 years older than us, or 100 million years older, and the math says many stars are old enough for exactly that, would be operating at a technological level we genuinely cannot picture. The gap would not be like us versus medieval Europe. The gap would be more like us versus an ant colony. Except we're the ants. That's not a small thought. Let it sit for a second. Now here is something that almost never gets mentioned when people talk about interstellar distances. The galaxy itself is not static. It is moving. Every star in the Milky Way, including our own sun, is orbiting the galactic center. Our sun completes one full orbit around the center of the Milky Way roughly every 225 million years. That means since the first dinosaurs walked the Earth, we have traveled less than a single galactic orbit. The galaxy is so old that some stars near the core have orbited it dozens of times. And all of this movement matters for interstellar navigation because a ship launched from one star system toward another doesn't aim at where the destination star is now. It aims at where the destination star will be when the ship arrives, thousands of years from now. Which requires a level of orbital mechanics calculation that makes landing on the moon look like catching a ball. The scale of what we're actually discussing is genuinely difficult to hold in your mind all at once. Every time you think you felt it, you realize you've only felt a corner of it. The rest is still out there, waiting to be understood. Chapter 2. What a civilization would actually need. So let's talk about what it would take. Not in the vague hand-waving way of science fiction, but in the actual physics and engineering way that researchers are genuinely working through. The first thing any civilization needs to cross interstellar space is energy. An enormous, almost incomprehensible amount of it. Let's take a ship about the size of a passenger aircraft. Not a massive generation ship, just something roughly equivalent to a Boeing 737 in mass, around 75,000 kilograms fully loaded. To get that ship moving at even 10% of the speed of light, which is the rough minimum for making interstellar travel even marginally feasible within a human lifetime, you would need energy equivalent to roughly 450 times the annual energy output of every power plant, every solar panel, every wind turbine, every burning fuel source on Earth, all combined for an entire year. That is not a rounding error. That is the scale of the energy cost at the low end. At 10% the speed of light, a trip to Proxima Centauri would still take about 42 years. If you want to actually get there within a single human working life, say 20 to 25 years, you need closer to 20% the speed of light. The energy cost climbs exponentially as you push toward higher fractions of light speed. This is because of something called relativistic mass increase. As an object approaches the speed of light, it doesn't just move faster. Its effective mass increases, which means you need more energy to accelerate it further, which increases the energy cost, which... You see the problem. The curve doesn't flatten, it keeps climbing. This is not a defeatist problem. It's a scale problem. And civilizations that have had millions of years to develop their energy harvesting could be operating at scales that dwarf anything we currently conceptualize. In 1964, a Soviet astronomer named Nikolai Kardashev proposed a framework for measuring civilizations not by their culture or technology, but purely by how much energy they can harness. It's called the Kardashev scale. A Type 1 civilization fully harnesses all the energy available on its home planet. A Type 2 civilization harnesses all the energy output of its star.
A Type 3 civilization harnesses all the energy of its entire galaxy. We are currently somewhere around 73 on that scale. We are not yet a Type 1 civilization. We have not fully captured even our own planet's available energy. But here's the part that makes you want to sit down quietly. A Type 2 civilization, one that can fully harness a star, would have access to energy equivalent to roughly 3 times 10 to the power of 26 watts continuously. Put it in terms you can feel. The average incandescent light bulb uses about 60 watts. A Type 2 civilization would have energy equivalent to 6,300,000,000,000,000,000,000 light bulbs all running at once. And they'd have it forever, for as long as their star burns. A trillion is 1,000 billions. Feel that for a moment. That number lives in a completely different universe from anything human economics or engineering has ever touched. At that energy level, the fuel problem for interstellar travel doesn't disappear. But it becomes the kind of problem you solve over a few centuries of dedicated effort, rather than a problem that stops you entirely. Then there's the propulsion question. What do you actually use to push a ship that fast? Our current rockets work by throwing mass backward very quickly. It's called chemical propulsion, and it's brilliant for getting off a planet's surface, but it's embarrassingly slow for crossing between stars. Even our most efficient proposed designs, like nuclear pulse propulsion, which would essentially detonate a sequence of nuclear bombs behind a ship to push it forward, top out at maybe 5% the speed of light, and that's with massive engineering challenges we haven't solved. The designs that start to make interstellar travel genuinely possible include things like laser sail propulsion, where an enormous laser array, potentially spanning thousands of kilometers and powered by something like a Type 2 energy source, fires a continuous beam at a lightweight reflective sail, pushing it up to a significant fraction of the speed of light. A project called Breakthrough Starshot has been seriously investigating this for sending small probes to Alpha Centauri within a human lifetime. It's real physics. It's not cheap, but it works on paper. Then there's the theoretical concept of a Bussard ramjet, proposed by physicist Robert Bussard in 1960, which would scoop up the trace amounts of hydrogen floating freely through interstellar space and use it as fuel for a fusion reactor. Space isn't completely empty. There are about 1 hydrogen atom per cubic centimeter of interstellar space. Not a lot. But if your magnetic scoop is large enough and your velocity is high enough, you could theoretically collect enough to keep accelerating indefinitely. The engineering challenges are severe, but the concept doesn't violate any fundamental laws. And then there's the strangest and most famous idea, the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. Instead of moving through space, it would move space itself. It would create a bubble of compressed space-time in front of the ship and expanded space-time behind it, allowing the ship to effectively surf a wave of geometry at any speed, including faster than light, without the ship itself ever violating the speed limit. The math works. The physics is internally consistent. The problem is energy. Early calculations suggested it would require more energy than exists in the observable universe. More recent refinements have brought that number down considerably, and a few researchers, including Harold White at NASA, have worked on optimizing the geometry to reduce the energy requirements substantially. Whether it's ever buildable remains genuinely unknown. But the point is that even faster than light travel doesn't live purely in the realm of fantasy. It lives in the realm of engineering problems we haven't solved yet. And a civilization 100 million years older than us would have had 100 million years to work on them. There is another propulsion concept that rarely gets the attention it deserves: antimatter rockets. When matter and antimatter meet, they annihilate each other completely, converting mass directly into energy with an efficiency that nothing else in physics comes close to matching. A matter-antimatter engine would, in theory, release about 10 billion times more energy per kilogram of fuel than the best chemical rocket. Think about what that means in human terms. If a car's fuel tank converted mass to energy at antimatter efficiency, a single tank of gas would be enough to power every electrical device in the United States for about 6 months straight. The problem with antimatter is that producing it is fantastically expensive with our current technology. We produce it in particle accelerators, atom by atom, and we currently produce about 10 nanograms per year globally. A nanogram is 1/1,000,000th of a gram. At that rate, producing even a single gram of antimatter fuel would take about 100 million years. But again, this is a production scale problem, not a physics problem. A civilization with a star's worth of energy available could crack the antimatter production puzzle in ways we can't currently model. The point of all of this is not that interstellar travel is easy. It is not. The point is that every barrier we identify, every challenge we articulate, is a barrier that falls within the domain of physics and engineering, rather than outright impossibility. And that is the most important sentence in this conversation. Chapter 3. The question of time. Here's something that doesn't get talked about enough. Time. Specifically, the relationship between how long civilizations might last and what that means for interstellar journeys. Even if a ship travels at 20% the speed of light, a trip to a star 1,000 light-years away takes 5,000 years. This is longer than all of recorded human civilization. The Roman Empire rose and fell in less time. Written language has only existed for roughly 5,000 years. So for a civilization to successfully complete an interstellar journey of even moderate distance, it needs to either send machines that don't age, send biological beings who somehow survive for thousands of years, send successive generations of beings who are born and die on the ship over many lifetimes, or find a way to travel so fast that the journey is short enough. Each option has its own profound implications. The generation ship is the one most people land on. A ship where the original crew grows old and dies, and their children carry the mission forward, and their children's children, for potentially hundreds of generations. This raises questions that go far beyond engineering. Questions about what it means to be born into a mission you didn't choose. About how culture and purpose survive across centuries in a closed environment. About whether the people who arrive at the destination 1,000 years after departure would even consider themselves the same civilization as the ones who left. Imagine being born on that ship. The stars outside the window are points of light exactly like they are for you now, except they're moving, very slowly. You grow up, learn everything your culture knows, have children of your own, and die, never having seen a planet, never having walked on soil. Your great-great-grandchildren, dozens of generations removed from anyone who remembers the home world, eventually decelerate into a new star system. Is that still the same civilization that launched? Does that question even have a clean answer? But there's a version of this that goes even deeper, and it's the one that tends to stay with you. Think about language. In the span of just 500 years, English has changed so dramatically that a letter written in the 1400s requires a specialist to read. 1,000 years ago, the language spoken in England was so different from modern English that it sounds like a foreign tongue entirely. Now, imagine a ship with 10,000 people that travels for 5,000 years. Whatever language they launch with will have evolved, fractured, and possibly splintered into multiple distinct dialects or entirely new languages by the time they arrive. The knowledge stored in the founding generation's books might become as difficult to parse as ancient manuscripts. The mission directives, the reasons they left, the culture they were preserving, all of it drifting with each passing generation like sediment through water. The ship that arrives might carry people who have only a myth-like memory of why they're traveling at all. And yet they'll step out into a new star system carrying, in their bodies and their genes and their partially remembered stories, something of the world that launched them. Whether that's enough to call it the same civilization is a question philosophy hasn't fully resolved, and probably never will. Machines don't have this problem. A robotic probe doesn't age. It doesn't need food or sleep or meaning. It can be repaired by internal systems. It can hibernate for millennia and wake up when it arrives. And if that probe carries enough information about its creators, enough to rebuild a civilization from scratch, then in some sense the civilization itself has traveled, even if no biological being ever made the trip. This is why some researchers studying the Fermi paradox, which we'll get to, suggest that the most likely form of interstellar visitors would not be biological creatures in spacesuits. It would be self-replicating probes. Machines that travel, arrive at a solar system, use local materials to build copies of themselves, send some copies onward, and begin study. Von Neumann probes, named after mathematician John von Neumann, who first described the concept in detail. At even modest speeds and replication rates, a network of such probes could spread across the entire Milky Way in under 10 million years. Given that the galaxy is over 13 billion years old, that's a blink. If anyone launched such probes even 100 million years ago, they've had enough time to cover everything, including here. Which raises the question that tends to make astrophysicists go quiet at conferences. Have they? There's one more version of time we should sit with before moving on. Something called time dilation. It sounds like science fiction, but it's been measured in laboratories and confirmed in the GPS satellites orbiting the Earth right now. If you travel fast enough, time literally passes more slowly for you than for the people you left behind. At 90% the speed of light, a traveler would age only about half as fast as someone at rest. At 99% the speed of light, the ratio becomes even more dramatic. At 9% of light speed, a journey that takes 1,000 years from the perspective of someone watching from Earth would feel like only about 45 years to the person on the ship. This means that in principle, a biologically mortal being could survive a journey of thousands of light years, as long as someone can build a ship that reaches high enough fractions of light speed. The people left behind would all be long dead by the time the traveler arrived. But the traveler would still be alive. There is something quietly heartbreaking about this. The ship launches. The people on the ground wave. Everyone they know dies. Their civilization changes. Their home planet is barely recognizable. And the traveler arrives, still relatively young, at a destination that has changed while they were in transit, with no way to go home to a home that no longer exists. The physics is one thing. The emotional weight of it is something else entirely. Chapter 4. The Fermi Paradox and the Great Silence. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. They were talking, as people at Los Alamos apparently did, about extraterrestrial life
and the likelihood that alien civilizations existed. And at some point, Fermi just asked a question. Simple, direct, devastating. He said, "Where is everybody?" Think about what that question actually contains. Galaxy is nearly as old. Stars began forming within the first billion years. Many of those early stars could have had planets hospitable to life. Given the billions of years available, given the billions of star systems, given that life on Earth arose relatively quickly once conditions were right, the expectation should be that the galaxy is full of civilizations. Some of them ancient beyond our ability to comprehend. Some of them capable of projects that alter the physical structure of entire star systems. And yet, silence. No signals. No visitors. No megastructures visible in our telescopes. Just us in the quiet. This is the Fermi paradox. And it is one of the deepest unresolved questions in all of science. There are many proposed solutions, and they range from comforting to quietly terrifying. Let's walk through the ones that matter most for our question of whether aliens could actually reach us. The first is what's called the rare Earth hypothesis. The idea that Earth is not typical. That the combination of conditions required for complex life, a rocky planet in a stable orbit around a calm star with a large moon that stabilizes its axial tilt, with plate tectonics that cycle carbon and regulate climate, with a gas giant neighbor like Jupiter that deflects incoming comets and asteroids, might be so uncommon that life of any complexity is extraordinarily rare. Maybe we really are alone, or nearly alone, in a galaxy that is physically capable of hosting billions of worlds but simply hasn't produced many complex biospheres. This is genuinely possible. We don't actually know how common the right conditions are. We've only found one example: us. And the sample size of one is not a data set. It's a story we're telling about ourselves. The second proposed solution is the Great Filter. The idea, originally developed by economist Robin Hanson in 1998, that somewhere in the progression from dead chemistry to star-traveling civilization, there is a step so unlikely, so catastrophically difficult that almost no species makes it through. A filter so fine that it catches nearly everyone. The question, the one that should make your chest tighten slightly, is whether the filter is behind us or ahead of us. If the filter is behind us, that's relatively good news. It might mean that the emergence of life itself is the hard part, or the development of the eukaryotic cell, or the development of multicellular life, or sexual reproduction, or any of the other transitions that happened on Earth over billions of years. It would explain the silence. Almost nothing makes it to the starting line, but we did. We are the rare exception. We are through the filter. If the filter is ahead of us, that's different. If the reason we don't see other civilizations is that something kills every civilization before it becomes capable of interstellar travel, then we have not passed the filter yet. We are approaching it. And whatever it is, nuclear war, engineered pathogens, climate catastrophe, artificial intelligence, or something we haven't imagined yet, it is waiting for us somewhere in our future. And it has ended every species that got this far. Some researchers have pointed out that finding life on Mars, or on Venus, or on any other world in our solar system would actually be very bad news under this framework. Because it would suggest life arises easily, and the filter is probably not in life's origin. Which means it's probably somewhere else. Somewhere further along. Somewhere we haven't gone yet. For now, our solar system appears to have only one living world. And that might be the most hopeful sign we have. The third proposed solution, and the one that keeps a certain type of scientist lying awake at 3 a.m., is the dark forest hypothesis. This idea was popularized by Chinese science fiction author Liu Cixin in his trilogy, but it maps onto real game theory in ways that astrophysicists have genuinely engaged with. The idea goes like this: resources in the universe are finite,
Any sufficiently advanced civilization knows this. And any civilization that reveals its location to another civilization has no guarantee that the other civilization is benign. The rational strategy in a universe of uncertainty and finite resources is to remain silent and, upon detecting another civilization, eliminate it before it becomes a threat. Not from malice, from survival mathematics. Under this model, the universe is not silent because it is empty. It's silent because everyone is hiding. And the civilizations that made the mistake of broadcasting their location were eliminated before they got old enough to appear in any historical record. The dark forest is a deeply unsettling idea. But it's not actually well supported by the physics and sociology that we understand. The energy cost of destroying a civilization across interstellar distances is enormous. And there's little reason to assume all civilizations would converge on the same paranoid strategy. Still, the thought lives in the back of the mind once you've heard it. It's the kind of idea that makes you wonder, on a clear night with too many stars, whether looking up and being visible was wise. The most popular serious answer among astrobiologists right now is the rare complexity hypothesis combined with the vast distances themselves. Life might be common. Microbial life, single-celled organisms, simple chemistry doing interesting things. But complex, intelligent, communicating life might be so rare that the nearest civilization to us is thousands or tens of thousands of light years away. Too far to have found us, too far to have reached us. And operating on timescales so vast that our 200 years of industrial civilization is a footnote too small for their instruments to reliably detect. We lit our first radio transmitter in the 1890s. We've been broadcasting into space unintentionally for about 130 years. Our radio bubble, the sphere of signals that has leaked out from our civilization, is only 130 light years in radius. Compared to a galaxy 100,000 light years across, that's like lighting a candle inside a room the size of a continent. And then wondering why no one in the far corner has knocked on the door. And here's a detail about that radio bubble that almost nobody thinks about. It's not uniformly bright. The signals we've been leaking are not coherent, directed broadcasts aimed at anyone in particular. They're the sloppy edges of television transmissions, radar pulses, and military communications spreading outward in all directions, getting weaker as they travel. By the time our signals reach even the nearest stars, they're so diluted by the inverse square law, the same principle that makes a flashlight less bright the further you are from it, that they would be almost impossible to distinguish from background noise. A civilization 50 light years away trying to detect us with technology equivalent to our own would hear something barely louder than static. We think of ourselves as broadcasting. We are more like whispering in a hurricane. Chapter 5. If they're already on their way. Here's where we have to sit with something uncomfortable for a moment. Not alarmist. Just honest. We have been a detectable civilization for about 130 years. But our solar system has been here for 6 billion years. And for the entire history of the Earth, the chemical signature of life has been visible in our atmosphere. Oxygen is what scientists call a biosignature. It shouldn't be there in the quantities we have without biology maintaining it. Any civilization with sufficiently advanced telescopes could have identified Earth as a living world from a distance. Without hearing our radio signals. Without receiving any deliberate communication. Just by looking at the light filtering through our atmosphere. Astronomers are already doing exactly this with exoplanet atmospheres. The James Webb Space Telescope is designed specifically to analyze the atmospheric composition of distant worlds. We have already begun detecting water vapor, carbon dioxide, and other molecules in atmospheres of planets orbiting other stars. The next generation of space telescopes currently being planned and designed will be able to search specifically for oxygen and methane, the double signature of a biosphere. If we can do that now, with our 130 years of technological civilization, a society 1,000,000 years older than us could have mapped every living world in the Milky Way before our planet even existed. We are not a secret. We have never been a secret. So if there is a civilization within several thousand light years of us that reached our level of technology even 1,000,000 years ago, and even 1,000,000 years is a blink in the age of the galaxy, they would have known Earth was alive long before any human stood upright. The question isn't whether they know we're here. The question is what they're choosing to do about it. There are a few honest answers. One is that they exist and simply aren't interested. A civilization 1,000,000 years old might find us about as compelling as we find an ant mound. Interesting, maybe, in a distant scientific way. Not worth the resources of an interstellar mission. Not yet. Not until we build something they can recognize as something other than noise. Another honest answer is that the travel time is so long that any civilization that decided to come here millions of years ago hasn't arrived yet. If our nearest neighbors are 50,000 light years away and traveling at 10% the speed of light, they've been in transit for 500,000 years. Their descendants might still be en route. We might be sitting here, having this conversation, while something ancient and unimaginable crosses the void between star systems, still 100,000 years out. There is no way to know. There is no telescope pointed in the right direction. There is no signal we'd recognize. There is just the silence and the math and the patient geometry of an old universe going about its business. But let's sit with a third possibility that tends to get less airtime. The possibility that they arrived here a very long time ago, found what they were looking for and left. Not because we weren't interesting, but because the mission was already complete. Imagine a scientific expedition in the year 1700 visiting a remote island never before contacted by European civilization. They observe the ecosystem, take samples, make drawings, interact perhaps very briefly or not at all, and return home. The island doesn't know they were there. The island never will. There is no monument, no signal, no obvious artifact. Just the fact of the visit, unrecorded by anyone except the visitors themselves. Our solar system contains billions of cubic kilometers of space, most of it completely unexamined. A visit like that, thorough, careful, and brief by interstellar standards, could have happened without leaving anything we'd recognize as evidence. And we've been looking at such a small slice of what's here. Chapter 6. The Physics of Arrival. Let's talk about what arrival would actually look like. Not the Hollywood version, the physics version. If a ship traveling at 20% the speed of light is inbound toward our solar system, we would have very little warning. Our ability to detect incoming interstellar objects is genuinely limited. We discovered the first confirmed interstellar object, the elongated rock called Oumuamua, in 2017, and only because it happened to pass close enough to the inner solar system for our telescopes to catch it. If it had passed through the outer solar system without getting close to the sun, we would never have known it was here. We are not watching the interstellar approaches to our system. We don't have the instruments.
We don't have the budget. We barely have the political will to complete a catalogue of near-Earth asteroids. A ship approaching at 20% the speed of light would cover 60,000 kilometers per second. That's fast enough to travel from the surface of the Earth to the Moon in about 6 seconds. It would cross the distance from Neptune's orbit to Earth in roughly 19 days. That's our outer solar system. 19 days. A ship could transition from the outer solar system to Earth orbit in a period shorter than most people's longest road trips. And before anyone gets anxious, here is what that number actually tells us. We are not facing any known inbound craft. The point is purely to establish that the distances we think of as protective aren't as protective as we imagine. Once something has crossed the vast emptiness between stars, the remaining distance within a single solar system is, by comparison, a very short walk.
Now, there's also a deceleration problem. Getting up to 20% the speed of light is hard. Slowing down again is equally hard, and in some ways harder. You can use laser propulsion to accelerate from home. But who's pointing a laser at your ship during deceleration? Some researchers have proposed using the magnetic field of the destination star as a kind of electromagnetic braking system. Others have proposed using the stellar wind to slow a sail. Others suggest carrying your own fuel for deceleration, which dramatically increases the launch mass and therefore dramatically increases the energy needed to accelerate it. This is the tyranny of the rocket equation. Every kilogram you want to slow down has to be accelerated first. And you need fuel to slow down the fuel. And fuel to slow down the fuel that slows down the fuel. The numbers spiral quickly. But again, not impossible. Just expensive. And solvable in principle, given enough time and energy and intelligence. There's another scenario that some researchers consider more plausible for very long journeys. Not a ship that travels from point A to point B, but something more like a seed. A small, dense package of information, biological or digital, that could be launched cheaply, travel for millions of years, arrive, and then reconstruct whatever it carries using local materials. Panspermia on purpose. Directed panspermia, which was actually proposed seriously by Francis Crick, one of the co-discoverers of the structure of DNA, who found himself unable to fully explain how life had gotten started on Earth, and suggested in 1973 that it might have been seeded deliberately from somewhere else. He wasn't being religious. He was being a physicist thinking about probability, and he never retracted it. The idea that our own existence on this planet might be the result of something like this, some ancient mission by some civilization so old it no longer exists anywhere in the galaxy, is genuinely unprovable with current tools. We can't read the genetic code well enough to find that kind of fingerprint. Or rather, we're just beginning to develop the tools to try. There is something that researchers call the biogenesis problem, and it's worth naming clearly. We don't actually know how life started on Earth. We have good guesses. We have plausible chemistry. We have RNA world hypotheses and hydrothermal vent theories and a dozen variations of each. But we have never been able to take a flask of early Earth chemistry and watch life spontaneously emerge from it. The step from complex chemistry to self-replicating molecules that evolve, the actual crossing of that threshold, remains one of the most genuinely mysterious events in the history of science. And the fact that it happened here once, very quickly in geological terms, within about 500 million years of Earth's formation, either means it's easy and we're the norm, or we got extraordinarily lucky. And those two interpretations lead to completely different conclusions about everything else we've been talking about. Chapter 7. What we would notice and what we wouldn't. Let's talk about contact. If something came here, how would we know? The honest answer is that it depends entirely on what came and what it wanted us to know. A civilization that wanted to be seen would be easy. Park something large enough in orbit, emit signals at frequencies we're already monitoring, appear in the daylight sky above a population center. We would know. There would be no ambiguity. Every telescope on Earth would lock on. Every government would scramble. It would be the single most important event in human history, and everyone alive would remember where they were. But a civilization that wasn't trying to be seen, or one that had sent probes on a pure observation mission, would be almost undetectable with our current capabilities. A probe the size of a large boulder, made of materials that don't reflect light efficiently, in a stable orbit beyond the moon, in a region of space we don't routinely scan. We could have one right now and have no idea. This is not a paranoid thought. It's an honest assessment of how much of our solar system we've actually looked at carefully.
The answer is a thin slice. The well-lit inner regions. The planets we can see. But the volume of our solar system extends far beyond Neptune, out to the Oort cloud, which reaches perhaps 100,000 times the distance from Earth to the Sun. That's a volume so enormous that if you printed the inner solar system on a piece of notebook paper, the full extent of the solar system would be a sheet the size of North America. And we've looked at that notebook paper. The rest is guesswork. In 2021, a paper by Harvard astrophysicist Avi Loeb and Amir Siraj suggested that Oumuamua, that interstellar object from 2017, had behaviors, specifically an unexplained acceleration away from the Sun that couldn't be fully accounted for by solar radiation pressure alone that were statistically unusual. Loeb has argued publicly and controversially that we cannot rule out an artificial origin for Oumuamua without better data. Most mainstream scientists disagree and prefer natural explanations. But the point isn't that Oumuamua was a spacecraft. The point is that we don't have enough information to be certain either way. And that uncertainty is itself the lesson. We spotted an unusual object, watched it for a few weeks as it screamed past us at roughly 87 kilometers per second, and then it was gone, into the dark. And we don't know what it was. That should be a small, quiet alarm going off somewhere in the back of your mind. What makes the Oumuamua story even stranger is that we almost didn't catch it at all. It was discovered by the Pan-STARRS telescope in Hawaii, and it was already leaving the solar system by the time we found it. We had days, not weeks, to observe it before it became too faint to study. Every telescope that could be redirected was redirected. And still, the data we collected was incomplete. It's a bit like trying to understand a stranger's entire life history from a single blurry photograph taken as they walked past a window. We don't know the shape of the thing clearly. We don't know its composition. We can make inferences and models, but the object itself is already billions of kilometers past us, on its way out of our solar system and eventually out of our galaxy entirely. We'll never look at it again. Whatever it was. In 2019, a second interstellar object was detected, called Borisov, and this one behaved more like a comet, shedding gas and ice as it warmed near the Sun, which made it easier to explain as a natural object. But the presence of two interstellar visitors in the span of 3 years after never detecting one before suggests that these objects pass through our solar system more often than we thought, which means the next one might come through while our instruments are better, and our ability to study it longer. And perhaps that time, the answer won't be as easy to put in a natural category. Chapter 8. The civilizations that could do it. Let's think concretely about what kind of civilization would actually be capable of reaching us. Not the nearest, not the youngest, but the ones that have had time to evolve past the struggles that currently define our limitations. There are stars in the Milky Way that are 10, 11, even 12 billion years old. If any of those early stars hosted rocky planets with the right conditions, life could have gotten started 8 or 9 billion years before it got started here. That's not just more time. It's a different category of time. If life had gotten started on an early generation planet 8 billion years ago, and if it had followed something like the trajectory we've followed, and if that civilization survived, and if it continued to develop, then by now, it would have had 8 billion years of technological development. We have had about 300 years, generously, if we're counting from the Industrial Revolution and the beginnings of modern science. If we are to them as a 300-year-old civilization is to one 8 billion years old, then their technology relative to ours is not further along. It's different in kind. In the same way that the telephone is not just a better version of a drum signal. It's a different kind of thing that operates on a different understanding of how reality works. A civilization that has had 8 billion years to develop could be working with the deep fabric of physics in ways we can't articulate yet. They might have solved the energy problem so completely that our question of fuel becomes like asking how long it takes to carry water from a river. A real question once. Now irrelevant. They might be living inside a Dyson sphere, a structure that completely surrounds their star and captures its full energy output, using the full power of an entire star as a continuous fuel source. A Dyson sphere around a star like our Sun would provide about 8 times 10 to the power of 26 watts of usable energy. Compare that to the current global output of all human energy use, which is around 2 times 10 to the power of 13 watts, and you start to feel how different the operating assumptions would be. They would have access to roughly 19 trillion times more energy than our entire civilization currently produces. Not twice as much, not 1,000 times as much, 19 trillion times. At that level, interstellar travel doesn't disappear as a challenge. But it becomes the kind of challenge you solve with logistics, not limitations. Like building a very long road. You still have to do it, but you have the equipment. And we should be honest about something else when we talk about civilizations this old. We're assuming they're still biological. We're picturing creatures something like us, with bodies and brains and intentions we can at least partially relate to. But a civilization 8 billion years old might have long since transitioned into something we don't have a framework for. Maybe they've merged with artificial intelligence in ways that blurred the line between biology and computation until the line disappeared entirely. Maybe they exist as patterns of information rather than physical matter. Maybe the concept of a body, of being located in one place, of having a lifespan, are all things they left behind billions of years ago. We keep imagining aliens as things that want what we want, that fear what we fear, that operate on scales of time and desire that we can recognize. But the most advanced civilizations, if they exist, might be so different from us that the question of whether they'd want to visit Earth is like asking whether you, as a human being, would want to visit a particular rock formation on the ocean floor. You might, out of curiosity. Or it might simply not be the kind of thing that registers as something to do. This is not a reason to stop thinking about the question. It's a reason to hold the question loosely, with open hands, ready to be surprised by the shape of the answer. Chapter 9. What contact would mean for us? We should be honest about what happens to a civilization when it makes contact with a significantly more advanced one. Not in theory, in practice. Because we have historical models, even if they're imperfect. When European explorers arrived in the Americas in the late 15th century, they encountered civilizations that had developed independently for thousands of years. The contact was catastrophic for the indigenous populations, not purely because of direct violence, though there was plenty of that. Mostly because of disease. Pathogens to which one population had no immunity, but which the other population had lived with for so long they'd developed resistance. An estimated 90% of the indigenous population of the Americas died within 150 years of first contact. Tens of millions of people. Not from war, from biology, from the simple collision of two worlds that had never touched. Scale that to the cosmic. If a biological alien civilization arrived here, the pathogen question becomes interesting in either direction. Their biology would presumably be so different from ours that direct biological contamination might not work the way it does when two populations from the same planet meet. But we genuinely don't know. The principle of caution that NASA applies to planetary protection, scrubbing spacecraft carefully before they land on Mars for exactly this reason, would apply in reverse. Something arriving from another biosphere carries an unknown biology into our ecosystem. And our immune systems have precisely zero prior exposure to anything from outside this planet's evolutionary history. But the more subtle impact isn't biological. It's psychological and civilizational. The simple knowledge that we are not alone, that something else is out there, something older, something capable of crossing the void between stars, would restructure something fundamental about how we understand ourselves. Every religion would be touched. Every philosophy of human uniqueness would need to be rethought. Every assumption about our place at the center of anything would quietly dissolve. And some of those assumptions are load-bearing. They hold up structures of meaning that billions of people navigate their lives by. This is not a reason to hope we don't find anyone. It's a reason to think about what we'd do with the finding, how we'd absorb it, what we'd become on the other side of it. There's a concept in anthropology called a paradigm collapse. It's what happens when the foundational stories a culture tells about itself turn out to be wrong in ways that can't be patched. Not wrong in small ways that can be absorbed into the existing framework. Wrong in large, structural ways that require the framework itself to be rebuilt. The last time something like this happened at civilizational scale was the Copernican revolution, when we discovered that the Earth was not the center of the universe and that our planet was just one of several orbiting a star. That shift took roughly 150 years to fully absorb. It produced enormous resistance, enormous fear, and ultimately an enormous expansion of what humanity was capable of understanding about itself and its place in reality. Contact with another intelligence would be a Copernican revolution happening in real time, over days or weeks, with cameras rolling and social media running and billions of people processing it simultaneously. We have never been tested at that scale before. We genuinely don't know how we'd handle it. But every time we have been forced to expand our understanding of what we are and where we are, we have eventually come out larger on the other side. Scarred sometimes, changed always, but larger. Chapter 10. The signals we're sending now. Here's something worth knowing. We are not just passively waiting to be found. We have already sent messages. In 1974, astronomers Carl Sagan and Frank Drake used the Arecibo radio telescope to beam a message toward a cluster of stars called M13, about 25,000 light-years away. The message encoded in binary the numbers 1 through 10, the atomic numbers of the elements that make up DNA, the structure of DNA, a picture of a human being, the structure of our solar system, and an image of the telescope that sent it. It was a 679-bit binary transmission, and 1679 is the product of two prime numbers, 23 and 73, which means any civilization with mathematics would immediately recognize it as intentional. M13 is so far away that any response, traveling at the speed of light, would take 50,000 years to arrive. So we're not waiting by the phone, but we spoke. Voyager 1 and Voyager 2, launched in 1977, both carry golden records. Physical discs made of gold-plated copper containing sounds and images of Earth. Music. Human voices in 55 languages. The brainwaves of a woman thinking about love. Greetings. Mathematical information. A diagram showing how to play the record. A picture of a man and a woman standing together with their hands raised. Those two spacecraft are now beyond the edge of our solar system and will eventually drift between the stars for longer than the Earth has existed. Barring some catastrophic collision, they will outlast our planet. They will outlast our sun. Billions of years from now, there is a chance, small but real, that something picks them up, plays the record, and hears us. We will be long gone. But the record will still be there, still spinning, still saying, we were here. We lived. We were afraid of some things and amazed by others. We made music. We loved each other. And we wanted someone to know,
Think about what it took to put that record together. Carl Sagan and his team spent months deciding what to include. They argued about what represented humanity. They chose music from dozens of cultures, from Beethoven to Azerbaijani folk songs to Chuck Berry. They included the sound of wind and rain and surf. A mother's first words to her newborn. A pulsar, one of the most precise natural clocks in the universe, to give any finder a reference point in time. And they chose the brainwave recording of Anne Druyan, who was in the early days of falling in love with Sagan himself during the project, thinking about the sensation of being alive and human and aware. That's what's out there, spinning between the stars right now. Not just data, not just science, but someone's heartbeat, someone's falling in love. Sent into the dark on a golden disc in case anyone was listening. That is one of the most human things we have ever done. Chapter 11. The Math of Probability. Let's look at the probability question seriously, because it's one that scientists have genuinely grappled with in mathematical terms. The Drake equation, formulated by astronomer Frank Drake in 1961 as a framework for a scientific conference on SETI, attempts to estimate the number of active communicating civilizations in the Milky Way. It looks at the rate of star formation, the fraction of stars with planets, the fraction of those planets that could support life, the fraction that actually develop life, the fraction of those where intelligent life emerges, the fraction that develop technology capable of detectable communication, and critically, how long such civilizations last before they go silent. The first few terms of the equation are now known with reasonable confidence. We form about 3 new stars per year in the Milky Way. The fraction of stars with planets is very high, essentially all of them. A reasonable fraction have planets in the habitable zone where liquid water could exist. The fraction that develop life is the huge unknown. So is the fraction that develop intelligence. But the most critical variable, the one that changes the answer from millions to nearly zero, is the last one. The lifespan of a communicating civilization. If civilizations, on average, last millions of years in their technological phase, the galaxy should be full of them. If they typically last only a few thousand years before destroying themselves or going silent, the galaxy might contain only a handful. Or none. Or just us. The honest answer is that we have one data point. Ourselves. And we've been a technological civilization for about 300 years. We don't know yet if we're going to make it. We genuinely don't know. We have the nuclear weapons and the carbon and the engineered pathogens and the developing artificial intelligence and all the other tools that could, with varying degrees of probability, end the experiment. We don't know which side of the filter we're on. But we also have the James Webb Space Telescope, the mapping of the human genome, the mRNA vaccine platform that could be turned against almost any pathogen within weeks, the growing renewable energy infrastructure, the beginnings of multi-planetary ambitions. We have the tools of catastrophe and the tools of survival, and we're choosing, every day, which ones to reach for more often. There's a newer version of the Drake equation that some researchers have started working with, and it asks a question the original didn't. Not just how many civilizations exist right now, but how many have ever existed throughout the entire history of the galaxy. When you run the numbers across 13 billion years of star formation and planet building, even with pessimistic assumptions about how rarely life and intelligence emerge, the cumulative count of civilizations that have ever arisen in the Milky Way becomes very large. The question shifts. Not are there others, but where did they all go? The galaxy should be full of ruins, of echoes, of artifacts left behind by species that rose and fell over billions of years. And if the galaxy is full of ruins, the silence isn't just strange. It's almost architectural. Like walking through a house that was clearly lived in, finding the furniture and the dishes still set for dinner, but no one home. and no note on the table. Chapter 12. The ones who might have tried. Let's be specific about who could actually make the journey. Not in fiction, in astronomy. The star Tau Ceti sits about 9 light-years from us. It's similar to our Sun in type. It has at least 5 planets. At least 2 of those are in or near the habitable zone. Tau Ceti is also significantly older than our solar system, somewhere between 5 and 6 billion years old compared to our 6 billion years. That extra 2 billion years is important. In our own history, 2 billion years is the difference between the first complex multicellular animals and today. An entire evolutionary revolution. If a planet around Tau Ceti hosted life that started about when life started on Earth, they've had one. 2 billion extra years to run the experiment. 1,200 million years. That's a number that swallows any analogy you try to build around it. The star Epsilon Eridani is about 10 light-years away. It's younger than our Sun, only about 800 million years old. Probably too young for complex life. But it has a planet, and it'll have billions more years. In billions of years, if something is still watching, Epsilon Eridani will be in the age range where its planet might host its own civilization, wondering if it's alone. These are our neighbors, the nearest ones. Out to 50 light-years, there are hundreds of sun-like stars. Many have planets. Some of those planets have been there for billions of years longer than ours. And we have looked at 0 of them carefully enough to know whether something there is looking back. One of the most haunting searches in the history of SETI happened in 2016, when astronomers using the Ratan 600 radio telescope in Russia detected a strong signal from the direction of HD 95086, a star system about 300 light-years away. The signal, detected at a frequency of 11 gigahertz, was unusual enough that it was quietly circulated among SETI researchers. It was not confirmed. It was not repeated. And the official conclusion was that it was likely terrestrial interference or a natural source. But there was a period of a few days when serious scientists thought they might have something. When they sat with the possibility. When the silence almost broke. HD 95086 is 300 light-years away. If that signal were a transmission, it would have left its source 300 years ago, in the 1700s, before the Industrial Revolution, before electricity, before we were listening. They would have been shouting into a world that wasn't yet ready to hear. And here's what makes that detail ache a little. If there really was a civilization 300 light-years away that tried to reach us in the 1700s, and if we sent a reply tomorrow, our reply would arrive there in the year 2326. Whatever civilization sent that signal would have been waiting over 600 years for an answer. That's longer than the United States has existed. That's the entire span from the early Renaissance to today. The beings who sent the original message would be historical figures by then. Their descendants, dozens of generations removed, would be the ones to finally receive our hello. And we don't even know if we should send it. The conversation across interstellar space is not a conversation in any human sense of the word. It's more like carving a message into stone and leaving it at a crossroads, then walking away, knowing that whoever reads it will be someone you'll never meet, answering someone who might no longer be alive. Chapter 13. The journey from their side. We've been thinking about this entirely from our perspective, our technology, our limitations, our search. But let's try to flip it. Imagine you are the astronomer or whatever serves that function on a world orbiting a star 500 light-years from ours. Your civilization is perhaps 10,000 years old in its technological phase. You have instruments that make our current telescopes look like the cardboard tube from a paper towel roll. You've already catalogued millions of planetary atmospheres across the galaxy. And in your survey, you find a small rocky planet, unremarkable at first, but with a spectrum that catches something in you: oxygen. In quantities that shouldn't exist without biology to maintain them. And methane. Methane that should react with oxygen and disappear within decades without a continuous biological source to replenish it. You've found a living world. You note its coordinates. You file your report. Your civilization debates what to do. Some argue for silence, for leaving it undisturbed. Some argue for observation. A small group argues for eventual contact. The debate takes centuries. Because your civilization is patient in a way that a species that has only had civilization for 300 years cannot fully conceptualize. Patience that comes from knowing you have all the time in the universe, and that hurrying has historically been the thing that breaks things. Eventually, you send probes, not to make contact, just to look. The probes take 5,000 years to arrive. By the time they do, your civilization has changed significantly. The specific people who authorized the mission are historical figures. But the probes arrive, settle into orbit around the living world, and begin their study. And they find something new. Something that wasn't there when they launched. This world now has cities, radio signals. It's become technological in the time the probes were in transit. The probe sends back data. Light speed, so it takes another 500 years for the data to arrive home. By then, 5,500 years have passed since anyone decided to look. Your civilization receives the news. The living world now has a civilization. And another round of debate begins. Meanwhile, on the living world, the beings there are just now learning to split the atom. They have no idea any of this is happening. They haven't even reached the moon yet. They are deeply, peacefully, unaware. That might be us, right now, in that story. We're the ones who haven't been told yet. And there's a version of that scenario that's even quieter and somehow more unsettling. What if the debate on the other end resolved in favor of non-interference? What if their ethics, built over 10,000 years of technological civilization, concluded that contact before a species reaches a certain threshold of development is harmful, not because they're malicious, because they've seen what happens? Maybe they've made contact before, earlier in their history, with species that weren't ready, and watched those species collapse under the weight of it, under the existential disruption of knowing they weren't alone, and decided never again. So they watch, they document, they wait. And from Earth, the sky looks completely silent, because it is, by design. Out of something that functions across an incomprehensible distance like care, here is what we've walked through, and here is what it adds up to. The distances between stars are genuinely crushing. They are not metaphorically large. They are physically, mathematically, overwhelmingly large in ways that take your breath away if you think about them long enough without looking away. Our best spacecraft would take tens of thousands of years to reach the nearest star. And the nearest star almost certainly has nothing interesting waiting for it when it arrives. The interesting places are much further. But the laws of physics do not forbid the journey. They tax it with energy, with time. With engineering problems so hard they make our hardest current problems look simple. But they do not forbid it. And a civilization old enough, patient enough, and capable enough, and the galaxy is old enough to have produced many, could find ways to pay the tax. Whether through generation ships, or self-replicating probes, or energy sources we haven't imagined, or geometries of space-time we're only beginning to write equations for. The silence is real. The absence of signal is real. And it is the deepest, strangest, most disturbing fact in science.
A universe that should, by the math, be full of voices and seems instead to be speaking only to itself in a language we haven't decoded. Whether that silence means we are alone, or we are hidden from, or we are simply not yet old enough to be spoken to, we genuinely cannot say. The honest answer is that we don't know. We have been a listening civilization for barely a century. We have been a detectable civilization for about the same time. Cosmic patience is measured in millions of years. We are a species that gets frustrated when a video takes more than 3 seconds to load. And every atom in your body, the hydrogen, the oxygen, the carbon, the iron, was synthesized in a star that lived and died before Earth existed. You are made of ancient fire. You are the universe's way of knowing itself. And somewhere out there, billions of light years of universe in every direction, the same thing is true of something else. Something that might be looking back. Something that might be patient. Something that by the math almost certainly exists. And by the silence almost certainly knows how to wait. We have been asking whether aliens could reach us. But maybe the better question is what happens inside us when we truly reckon with the possibility that they could. That something old enough to have solved the problems we're struggling with right now might be watching a young, bright, noisy civilization working through its adolescence on a small, warm planet, third from an ordinary star. The same way you might watch a child trying to solve a puzzle they'll figure out eventually. With patience, with distance. Maybe with something that functions like affection. Or maybe not. Maybe the silence is the silence of emptiness. And we are the universe's only attempt at looking at itself this clearly. That thought is either the loneliest in the world or the most sacred. And right now, in this moment, with everything we know and don't know, we can't be sure which one it is. Both feel true. And sitting with both at the same time is as close to wisdom as the question allows. On a clear night, away from city lights, you can see a faint smear across the sky. It looks like someone dragged a pale finger across the dark. That's the Milky Way. That's home. All of it. Every star you can see and 100 billion more you can't. Every world we found and every world we haven't. Every possible origin story and every possible ending. All of it, curving overhead, patient and ancient and burning quietly. Our sun has been burning for 6 billion years. It has roughly 5 billion more before it exhausts its hydrogen and begins to expand and eventually swallow this planet. Whatever we are going to become, we have time. Not infinite time. But enough time to be genuinely different from what we are right now. Enough time to solve the problems that currently feel permanent. Enough time to find out what's out there. Or, if nothing is out there, to become what someone else would have been. We are 300 years into a journey that might last millions. That is not a reason for despair. That is the most hopeful thought I know. We are so early. We have barely begun. The universe is still mostly ahead of us. And the question of whether we'll make it, whether we'll find anyone, whether anyone will find us, is a question that will be answered. Just not by us. By whatever comes after us. Whatever we manage to become. Carrying everything we figured out, everything we made, everything we loved and lost and tried to explain to each other. And maybe that's enough. To be part of the attempt. To be the generation that first started truly listening. To have lived on the planet where the conversation began. But here's the question that scientists are genuinely uncomfortable discussing in public. If an interstellar civilization had been watching Earth for millions of years, since before complex life existed here, they would have watched an entire evolutionary story unfold in real time. The emergence of fish, of land animals, of mammals, of us. And if they were truly patient, if they were truly advanced, the question isn't whether they'd find us. The question is whether they've already decided what to do next. Whether there's a protocol, a threshold, some level of technological development or environmental signal that triggers the next step in whatever process we're completely unaware of. And the deeply strange thought is this: we might have already crossed it. Something we did in the last 300 years, something visible from outside our solar system, might have already changed our status from observed to something else entirely. And we have no idea. No framework. No instruments. No language yet for what that would even mean. If that thought is still living in your chest somewhere, you're going to want to watch the next video right here, because it goes somewhere darker and more specific.